single replacement reaction, we want to be able to write a net ionic equation as opposed to the molecular equations that you would have written in honors. So as mentioned previously, we're picking up a little bit into this. Remember that you are going to want to get to a net ionic equation. And if you have a metal, you will react it with the cation that was part of the ionic compound, and you'll generate a new cation and a new metal. So in looking at this equation here, we have calcium reacts with zinc chloride. So how do we write calcium? Does it need a charge? No. All right, that's a metal off the periodic table, an element. Now it's going to react with zinc chloride. So are you going after the cation component or the anion? Cation. And zinc always has what charge in a compound?
2 plus.
2 plus. And what are we going to form?
Calcium ion.
And zinc, the metal. What's the oxidation number of zinc?
0.
And what you can see here as well is single replacement reactions are examples of redox reactions. Okay, and we talked about redox prior to our extended hurricane break.
Wait, how do you know, like, where'd the chloride go? How do you know that?
The chloride ion is the spectator ion, and in a single replacement reaction in which you have a metal, the anion will be the spectator ion, and it wouldn't be included in the net ionic equation. Okay. The second example I gave you in your notes is an example of no reaction. They won't give you one like this, but tell me why this would be no reaction.
Sodium has a higher activity than cadmium.
Exactly. Sodium's activity is higher than that of cadmium, so cadmium does not have the ability to displace sodium. The cadmium is here and the sodium is here. Good. You won't see those. Let's take a look at C. It says sodium reacts with a solution of cadmium bromide. How do we write sodium?
Na.
Na. Cadmium bromide. We're going after the cadmium ion. Cadmium is in the same group as zinc. What's cadmium's charge always? 2 plus is correct. What are we going to generate? Good. Now that's not balanced because you can see 2 pluses here and 1 plus here. So what do I need to put in front of the sodium ion? You got it. Balanced. I would like you to try D. You are picking up on this very quickly, which is a great sign. We have magnesium reacts with a solution of aluminum chloride. And it did ask for the oxidation number of the solid product as well, so we'll hit that. Give it a shot. It's highlighted on in yellow on the screen. Excuse me. This one's a little bit of a stinker to balance, so just have patience with it. Did you get what I got? Yes, yes? Oxidation number of the aluminum is 0. What would be the total number of electrons transferred in this one?
6.
6 would be correct. You have 6 pluses on each side, so you need 6 minuses. All right. The other point I want to make in this type of single replacement, and remember with single replacement you can have metallic or non-metallic. So in finishing up the metallic, I just want to remind you that whereas hydrogen is of course not a metal, it is a part of the activity series. So metals above it can displace proton, and it's displaced as hydrogen gas, and that's why I have H2 here just as a reminder. You can see this in the first example. It says aluminum reacts with hydrochloric acid. Now hydrochloric acid is of course a strong acid, so proton and chloride ion. And you could go back into the old honors method, or you can jump right to the net ionic balanced equation. If we look just at the net ionic equation, you can see aluminum reacting with proton to generate aluminum ion and hydrogen gas. Be very careful with the hydrogen gas generation. And then to balance it off, it's a little tricky. You have 1 plus and 3 plus, but you have 2 of these, so you've got to balance it off. But we'll hit another one just like that, so you'll see it. Let's look at this one. You want to give it a shot?
No.
Why not?
Very tired.
Come on, we can do it. It says magnesium reacts with nitric acid. Try it. Yes, you do.
I don't know what nitric acid is.
It comes from 8, so think about a nitrate ion. That's from the summer assignment.
Probably. I don't know what's going on.
Can we focus on what we're doing, please? I know we've had a very long, trying hurricane break.
I'm still confused how to figure out which is the spectator.
The spectator ion in these metallic single replacements is going to be the anion of the ionic compound. So for example, in this one, the spectator ion is going to be the anion of the ionic compound. So in the one I've just given you, how do you write nitric acid? How do you formula write that? HNO3, right? So the spectator ion would be nitrate ion, NO3 minus. So in this one here that I just asked you to do, you have magnesium plus proton. Remember, as proton gets bumped, it's generating hydrogen gas, and the spectator ion would be NO3 minus. We'll do another one. Let's try this one. Let's say we had calcium reacts with perchloric acid. Sulfuric is a whole can of worms we don't want to play in right now. So how would we do this one? Calcium. Is perchloric acid a strong acid? Yes, it is. So this is perchloric acid, but we're only going after the proton, the cation. We're going to generate calcium ion and hydrogen,
Yes.
gas. And then we just have to balance. And in your lab on gases, not the lab we do next week, but the lab after that, you'll be reacting magnesium with hydrochloric acid. And you'll generate hydrogen gas and we'll collect that in a eudiometer. Very cool. All right, so for single replacement, we've got the metal variety in which you're going to have metal plus metallic cation yielding a metallic cation from here and a metal from here. The other type we have is the nonmetal, specifically the halogen replacement. And an activity series exists for this too. It's very simple. It goes straight down group 17, where fluorine has greater activity than chlorine, greater activity than bromine, greater activity than iodine. For example, what you would have seen last year, fluorine gas reacts with sodium chloride. This time you're going to bump the back end out. We're going to generate sodium fluoride and chlorine gas. But in a net ionic form, and we'll go through all the steps here so you can see the spectator, and we'll show you how to really get it down quickly. What would the spectator ion be here? Sodium ion. So in non-metallic single replacement, you're going to, have the halogen plus the anion. So halogens are nonmetals. Nonmetals gain electrons, forming anions. So you're going to have the halogen and the anion. The cation will be the spectator ion, and you would balance off. And we'll walk through several of these. This whole section in your notes I canceled out. I don't think you'll see anything like it, so we won't play there. The activity series of nonmetals, as I said, if you have liquid bromine and you shake it with a lithium iodide solution, this is how you would have written it out at the honors level. This is how you're going to write it out at the AP level. The cation is the spectator ion. It's not included. Similarly, chlorine gas is bubbled through a solution of sodium bromide. You're going to get rid of the sodium ion because that is what type of ion? Spectator ion, the cation. And you have this. Let's walk through several from scratch. It says fluorine reacts with cesium iodide. I want to know which substance gets oxidized. How do I write fluorine? It reacts with cesium iodide. Am I interested in the cation or the anion? Anion. So I'm going after the anion only. The halogen generates a halide ion. The halide ion generates the halogen, and we balance it. And the spectator ion in this case of fluorine reacting with cesium iodide would be what? Cesium ion. Make sure it has a charge on it or it's not an ion. Which substance gets oxidized? What does it mean to be oxidized? Do you lose or gain electrons? You lose. Leo. Guys, you had 7 days off. You had to master what we already did. Oxidation is a loss of electrons. So from 0 to -1, are you gaining or losing electrons which are negative? Gaining. So the substance that gets oxidized would be this one, the iodide ion. The next one says chlorine gas at the top of the screen. Chlorine gas is bubbled into a solution of potassium iodide. Try it. What'd you get? Did you get what I got? Yes? Yes, yes? All right, I want you to try these two right here.
How did you put the two?
Here?
To balance for charge.
Well, it was balanced for charge initially, but you have 2 CLs here, so you need 2 here. All right, try those two.
Put this here.
Chris, you ready?
Is it the one that gains electrons?
I can't hear you. What?
Is it the one that gains electron or loses electron?
Is it what? I just want you to write the net ionic balance chemical equation. Did you do it?
It's always.
There's the first one.
I can only see the reactants.
Say what?
I can only see the reactants.
There's the second one.
Wait.
Don't look up.
You put your hand over it like Mr. Monk.
Mr. Mark
He
freezes
freezes
his
his hand.
hand and it looks so creepy.
Like he puts his hand there and freeze it and clicks freeze.
Freeze it.
No, now your arm's on there.
You still can't see it.
Okay, I see what you did.
Ha, that's kind of cool.
We showed you that last year.
I know, but I forgot.
You kept trying to like keep your hand over the answer and walk into your room. And you couldn't do it. She was like,
I'm
"Try
done.
to walk over there."
The last sticker.
Nick called us.
Look at my little finger up there. It's so funny.
Okay, freeze your hand.
Where's the second one? Under her finger.
No, no, the second one's here. I didn't show the answer yet.
Don't show it.
Are you ready?
Don't look up.
Just totally.
Single replacement. I think you think that single replacement's very easy, which is wonderful. I hope you find it this easy. Kids usually have the most trouble with the single replacement.
Really?
It's easier than double replacement.
Cool.
Good for you.
All right. With the single replacement,
Are we doing combustion?
hang on. With the single replacement, classwork, and we're not done yet. We have a smidge more to do, and then you're going to have a lot of practice time. With the single replacement, classwork 1.4, it's a whole big packet. The D portion has several problems. We can work through a few of them together now. Also, with the single replacement, the POGL packet I gave you has some good insight with single replacement, and you'll have time to work on that as well. Please remember that single replacement reactions are also redox reactions. Another type of redox reaction, which we've already covered, is combustion. So I'm not going to do that again. The last piece I want to go over is synthesis and decomp, and that'll look a little murky at first, but I don't think you'll find it terribly challenging. Let's see how good you are with single replacement. If we look at classwork 1.4D, that's the single replacement stuff. If you look at what shows a page 46 there, it's going to be toward the end of the packet. I want you to try 2 and 3. See if you can do those.
For now?
Yeah. Well, or would you rather do it at the end of the lesson? Let's make sure you can do it. 2 and 3, go. Well, if you can't find it, it's right there on the screen.
This is not this one.
2 we already did 3 times. All right, are you done? Why not?
Don't even bang it. Just look at the screens.
Hey, be nice to each other. Gosh, we had a hurricane and you guys are crabby.
Did anybody celebrate the survival?
Shh,
I did.
do your work.
Yeah, it really is when it's still
I don't know how to do it.
It's still diatomic, I promise you.
No.
Yes, it
gas
is.
one.
Yes, it is.
That would be.
Sprinkle.
It's still
Yeah, that's for
diatomic.
gases.
It's still diatomic. She just wrote it on the screen like 5 seconds ago.
What's the difference? What's the difference if it's diatomic or not?
The molecule still bonds to itself just because it's a liquid doesn't change it. Well, now it's looking very far.
I don't want to, but I could use something now.
Miss Vera, what's the question? Is it?
Liquid bromine is still
How do you know
right?
whether we are?
Yeah. I didn't know that was.
How do you know whether to write? Like,
I don't know what that shirt is.
no, she's. Look, it's like, I don't know whether to write AL. I am so AL.
It's just aluminum strip. You can't have a strip you have
Because I was talking about they have it like origin.
in the left side, and then you get to the right side.
If there used to be music on the side,
Or actually, no, you won't have a link. Oh yeah, yeah.
we could bring it back.
Yeah, on the right side.
No, you know, obviously it's a real thing.
Yeah, I'm sure there's a state run.
The only one I've seen.
No, wait, no, wait, yeah.
Can you at least bring it here?
Roger Taylor, liquid bromine is still BRT, right?
Yeah. All right, this is what I got. Had to have a quick pee-pee break. That's why Mrs. Vera watched. All right. Yes, yes? All right. Good, good. Let's put single replacement to rest for a little bit. Go ahead.
How do you know which one's oxidized? I didn't get it when you were talking
Oh,
about it.
the substance that's oxidized loses electrons. So these are both 0. These are -1. So to go from 0 to -1, electrons are negative, so you gain. So the bromine is reduced, and this one lost, so this is oxidized. And that's from the lesson on redox that we did prior to Hurricane Irma.
You know, there might be another one hitting us next week.
Can't wait. All right.
Well, it's not yet scheduled to
Scheduled. Like the meteorologist, like schedule it.
You know what I mean? It's not projected to hit us.
You know, we're gonna.
Alrighty. Last but not least.
He's like, I can relate.
Wait, Dr. Taylor.
Hang on. Last but not least,
Hasn't made it to clinic yet.
we have covered reactions in aqueous solutions. We have talked about double replacement with precipitation. We talked about acid-base reactions with titration. We talked about redox reactions and the complex balancing, which hopefully you have mastered. On your quiz, scheduled for Wednesday, there will be one redox reaction to balance in part 2. And then there will be multiple questions about that equation. How many electrons are transferred, which substance gets oxidized, as well as writing some other types of simple equations. We've talked about single replacement, and the last thing we want to talk about is synthesis and decomposition. The synthesis is going to look pretty similar to last year. There's going to be a little bit more complex synthesis, but nothing that's going to bother you. The decomp is also very straightforward. And we'll go through this for about 15 minutes, and then we'll have a good 45 to 50 minutes to practice to hammer out these sections we've talked about today, as well as anything you feel like you need a little more assistance with. Clearly, to prepare well for the quiz, you want to make sure you can do that entire practice quiz with ease. but also the balancing of redox will be critical. All right, with synthesis and decomp, I'm just going to do this right off the classwork packet. We already talked about combustion, so I'm not concerned there. And some of the other practical applications, very interesting for those of you potentially interested in food chemistry, nutrition, things like that. You'll actually find these redox reactions to be very worthwhile in the long run. And if you're not sure what you want to do, but you're interested in chemistry, I highly recommend certain fields. I think they're very worthwhile, very profitable, and all that good stuff. All right, with synthesis and decomp in your packet, these are going to be the last 2 pages. And I want to go through several of these with you and then show you how to work them. They'll look a little tricky with you at first, but I don't think you'll find them that overwhelming. Challenging maybe, but not overwhelming. All right, with synthesis, we know this is like getting married. Girl meets boy, and they become a couple. And for the most part last year, we kept this very, very simplistic, where you might have magnesium reacting with oxygen gas to generate magnesium oxide, and you just had to remember to formula write your products. But for the most part, you started with 2 elements, you smacked them together and made a compound. You'll see that type of arrangement in the first one, but the other ones are really a little more complex, where you have 2 compounds reacting to form a more complex one. So A and B can be elements and or compounds, so be careful there. This will be a compound that's more complex than what you started with. The first example is similar to what I penned out. It says a metal combines with a non-metal to form a binary salt, and this you would have seen previously. Lithium reacts with nitrogen gas. Formula write your product, otherwise you are going to make a mess. I don't think you would have an issue at your level. Keep in mind, lithium group 1, nitride group 15, swap drop, lithium, nitride, and balanced. So a metal and a non-metal make a binary salt. And again, there's nothing different there than what you learned in honors. Here's where a few of the differences come in, but it's not going to be overwhelming. We're going to focus on metallic oxides and water and non-metallic oxides and water. What you're going to see is that the non-metallic oxides, when they react with water, they're going to form bases. Just remember MOB, M-O-B. Metallic oxide with water forms a base. If you have, for example, sodium oxide and water, you're going to form the base sodium hydroxide. Now, it's
So that way you can see the hydroxide.
it's a little easier to see that the NaOH, you can see the base formation, the Mg, the OH, you just see the base formation, but you would write H2O. If you form a strong base that's a group 1 hydroxide or a CBS, calcium, barium, or strontium hydroxide, you will need to ionize the base. Strong bases ionize completely. This is a weak base, so you don't. So a metallic oxide in water makes a base. A metallic oxide in water makes a base. A non-metallic oxide like carbon dioxide, dinitrogen pentoxide, nitrogen dioxide, sulfur dioxide, etc., and water make acids. If you make a strong acid, you will need to ionize it. Let's look at a few more of those. Let's say, for example, that you have calcium oxide and water, or you have sulfur dioxide and water. You have a metallic oxide and water. Just remember the mob. A metallic oxide and water forms a base. What base would you form? Now, is calcium hydroxide a strong or a weak base? Strong. So you wouldn't leave it as a unit, but rather in its ionized form. Is this a metallic oxide or a non-metallic oxide? Non-metallic, and they're going to make an acid. NMOA. I don't know. So that's going to make what? Sulfurous acid. Weak or strong? Weak or strong? Weak. So leave it together. Tell me what this makes.
Do you balance?
That is balanced. They very often come out balanced.
Is that NO2 or NO3?
NO2.
How do you know if it's weak or strong?
You need to know your strong acids. You have HCl, HBr, HI, nitric, chloric, perchloric, periodic, and sulfuric. Those are your strong acids. In your notes and in your packet. Your strong bases are going to be your group 1 hydroxides and calcium hydroxide, barium hydroxide, and strontium hydroxide.
May I take a picture?
No.
I don't care. I just don't want to be in it.
Duck.
Goose.
I think you should dot.
You should have been a
I'll make another one. Oh, never mind.
All right. So what does this one make? What does it make?
Nitric acid. Nitric acid. Oh, it makes proton and nitrate.
Nitrate
I got it.
How do you know it was a fat H?
Because there's O2 and then the other O.
Your H is so fat.
I was writing at a funny angle. I'm sorry.
Doesn't it make proton and nitrate?
Yes. Because it's a strong acid. That one you'd have to balance off.
Yeah, that one was the hard one we couldn't balance with white.
Yeah, you never went back.
we never
to that.
finished
Oh,
that.
yeah, you never
Oh,
did it.
never mind, I never mind.
All right, we'll do it.
She was like, oh,
I don't remember which one it
I
was.
have it.
All right, we'll come back. All right. A metallic oxide and water makes a base. A non-metallic oxide and water makes an acid. If it's strong, you have to ionize it. The other thing you can do is you can react metallic oxides and non-metallic oxides together, and they're going to form salts. And these are good to know because this will, if you work it backward, lead right into your decomp. So a non-metallic oxide such as carbon dioxide and a metallic oxide such as sodium oxide will make a salt. Same thing here. The reverse of synthesis is decomp. This would be like getting a divorce. You're going to break things apart into simpler substances. When you have a decomposition reaction, you're always going to have one reactant. You're going to generate 2 or more products. And you can see that this decomp here is the reverse of here. So when you have a metallic carbonate, you're going to generate a metallic oxide and a non-metallic oxide. So if, for example, I gave you calcium carbonate, you have a metallic carbonate, what would you generate?
Carbon
Carbon
dioxide,
dioxide, calcium
calcium
oxide.
Yep. Metallic oxide, non-metallic oxide. if you have a metallic chlorate, you're going to get a metallic chloride and oxygen gas. So if you have a metallic chlorate, you'll get a metallic chloride and oxygen gas. For example, if you had potassium chlorate, what would you get?
Oxygen gas.
That's not balanced.
No.
Thank you.
Now it is. This one's a little funky. I don't think you'll see anything that difficult. We won't worry about that one. And then these are very interesting because these are the reverse processes that we looked at previously. If you have sulfurous acid, you'll get sulfur dioxide and water. So this is the exact reverse of the acid formation. Same thing here. If you have carbonic acid and you decompose it, you're going to get water and CO2. I'm not worried about this electrolysis at this stage of the game. We'll worry about that later. This is one that does come up sometimes. Hydrogen peroxide always makes water and O2. And this one you have already seen. We talked about that one previously. Let's say, for example, you have well, this is the most common one. If you have this, it yields what?
Carbon dioxide.
Water and CO2, right? And if you have this, it makes SO2. Those are the only two they ever ask. I don't think you need to know anyone. All right, let's take a look at it all mixed up, because this is when it gets cranky-wanky. It's the last piece. Let's do the first four together. Ready? The first one says a sample of calcium carbonate is heated. So what would that be? When you heat something, you typically go like that. Triangle means heat. So what would that make?
CaCO?
No, calcium oxide and
It makes two oxides.
it's carbon dioxide.
I know.
Oxygen gas.
I know.
All right, the second one says sulfur dioxide gas is bubbled through water. What are you going to make? Sulfurous acid, weak or strong? Weak, leave it together. Solid potassium oxide. Whenever they say solid, I'll always put an S here, and that tells me not to touch that compound. CO2. You have a metallic oxide and a non-metallic oxide. You're going to make a salt. What's the salt? All right, Tyler, if you have hydrogen peroxide, what are you going to make when you warm it?
That's a tricky one.
Oh my
I don't know.
Bro.
I'm so confused. Water and oxygen?
And how'd you figure that out, Chase?
My name's not Chase.
I know, but he told you, so.
A little birdie whispered it to me.
Oh, she's actually asking me. I thought she was asking Tyler. I guess. Okay.
No, this is one that you also want to know. This is one that they can commonly ask, and the reason why they ask it is there's so many fun questions to ask about it. What's the oxidation number of oxygen and hydrogen peroxide?
-1.
Correct.
And also, doesn't hydrogen peroxide decompose from light exposure?
Yes, that's why you have it in a dark bottle. Let's do one more. 5 says lithium oxide. You do this one.
Thank you.
Alright, I got this one. That's me.
You're good at it though.
What do you left there?
I guess you're easy.
All right, do number 5.
Lithium oxide.
It's on the screen. It's underneath the boxed one.
Wait.
You get amine and hydroxide.
How'd we do?
Ready?
You want another one of those?
Yes.
All right, so I'm just going to add a couple here. Try those 3.
What is that?
Can't read my handwriting?
No, what's the
No,
secret?
carbon dioxide,
And,
0.
and.
That's how you write your zeros.
I know, but the 0 has a slash that way.
You too, Ryan. You too. That was funny. CO2.
Don't worry about it.
Huh?
If you have
All right, so did you get that?
It wasn't right anyway.
So I froze my
I wasn't
screen.
feeding myself to embarrass myself. Said it once, nobody heard me. We're good.
I need to.
I gave up.
All right, how we do? You ready to look? Not yet? Here's what I got. Did you get what I got? How come I didn't ionize magnesium hydroxide? Because it's not strong.
I do that.
all group 1 bases and CBS.
You're good? To prepare well for your quiz, classwork 1-4 needs to be done. The POGO packet needs to be done. The practice quiz from beginning to end. For those of you on the previous quiz who didn't do part 3 in preparation for your quiz, You made a mistake. Make sure you do all of the practice quiz. Questions here?